Hi guys, my name is Adam. Today I'm here to talk about Zen, smart contracts, what a blockchain, how it works, and how Zen is different. Before I cover that, I want to talk about what I think blockchains are good for and what they're going to be used for. So I think there's been a lot of focus on maybe blockchains being used for decentralized applications, maybe them being used for something else. But essentially, blockchains are best for moving an asset under some set of conditions. So what we're doing is we're saying essentially, let's replace banks, for example, with a contract, and that contract will release the assets to your counterparty if some condition occurs. Now, I want to compare this to how Bitcoin works. A lot of people maybe think that Bitcoin doesn't have smart contracts, but that's actually not true. Every Bitcoin transaction is essentially a smart contract. Bitcoin works by having what we call an input-output paradigm. So you own outputs and you send inputs. And when you create a transaction, essentially, you take your output, turn it into an input, and then create an output to the person you're sending to. Now, for example, if I was sending this transaction, where you see the unlock condition, is where I would create a proof that answers the requirements of the software program. So for example, maybe someone locked money to me, and what I need to prove is that I own a private key that correlates to a certain public key it was locked to. So when I pass these transactions on to miners, they're going to do essentially three things. The first thing they're going to do is they're going to evaluate, is the input greater than the output? That's the first condition. The second condition they're going to do is they're going to check if it's been unspent, so if the output exists in the UTXO set. And the third thing they're going to do is they're going to take the transaction and they're going to put it on a stack, and that's like Bitcoin's computation paradigm, and they're going to evaluate it on the stack. And if it returns true, then the transaction's valid. Now, because every Bitcoin transaction essentially holds its own software program in it, what that means is that you have you can essentially see the size of the software program by looking at the size of the transaction. And because Bitcoin doesn't have things like loops and recursion, you have a good estimation from the size of the transaction how complex it's going to be for miners to validate that transaction. So you have a linear relationship between complexity and size of transactions. Now, another smart contract platform is Ethereum. Ethereum doesn't work like Bitcoin with transactions. Ethereum is essentially a message-based platform. Ethereum essentially is a virtual machine. It takes Bitcoin's design of a stack. It adds into it the support for like one asset, like Ether. And then when you want to do a computation on the EVM, you essentially take your Ether, you convert it to gas, and you start doing a computation. So essentially what's happening is someone's coming along and saying, OK, I want this contract to do something. And then that contract may, if enough gas was provided to it, the contract will change the state of the EVM and the compute, and that's essentially what's going on. A few things that Ethereum has done with their design is that, number one, they wanted to facilitate a very generalized platform for like Uber or Facebook on the blockchain. And in order to do this, they wanted to have contracts be able to call into each other. So for example, like your Uber contract would be able to talk to your alarm clock contract. And the second thing they've did is they wanted to have more complex conditions. So they wanted to be able to say something like, they wanted to have things like loops and recursion and a friendly developer language, which is very similar to JavaScript called Solidity. And in order to do that, there was no way to essentially measure the cost of the computations for miners. So what they did is they said, listen, we're going to have this counter, which is gas, and it's going to count each computation you do. Now, if we look at our paradigm versus something like Bitcoin, we're very, very similar. The main difference is, as you can see, we have support for multiple tokens rather than just one token. Also, unlike Bitcoin, our contracts live independently of the transactions. So you'll have a transaction here, but the validity of that transaction not only will depend on the inputs being greater than the outputs and the UTXO set, but rather it will also depend on if the contract says it's valid. And the third thing that we're different with Bitcoin is that we can operate on more complex conditions. So we can have things like recursions and loops and still be able to know the cost of those transactions, which I'll cover a bit more later. But it's not only being able to program more complex conditions using recursion and loops, it's also being able to operate on complex conditions, such as, for example, being able to determine that I'll only send an asset if the price of Apple is above a certain price, like essentially creating collateral or in call options and those kind of things. So again, Zen's a UTXO paradigm. So when you look at it compared to Ethereum, what are the differences? Or not only Ethereum, any VM. It could be something like Rootstock, or there's a bunch of Ethereum 2s now that are out there. So the first thing is that we're not a virtual machine. So with us, each of our contracts live separately. They're not in part of a much larger entity, like a contract is in Ethereum. They live separately. And the other thing is that because they live separately, there's no way to count the cost as in Ethereum, so we use a formal verification for that. So how do we determine the cost of a contract ahead of time? Well, what we do is we write code in F star, or the developer would write code in F star. Then what would happen is our software, our solution essentially automatically finds these proofs for you. It says, okay, we can know that, let's say there's a cost function where the cost of executing this computation for a given input is, let's say, the length of the input squared plus 100. So that's what a cost function looks like. And you have to prove that this cost function matches the contract before you can insert it into the active contract set, which is essentially something like our execution paradigm. Noteworthily, if you look at, let's say, Bitcoin, each time that you start to execute each time you try to execute a contract, you're essentially creating a new stack. You're pushing things onto the stack, and you're validating. But with us, essentially, the contracts are always there. So they're sitting compiled into the user's computer, just like any sort of a maybe game or software program you currently have on your desktop, and we're just providing an input, and it's returning an output. So a quick recap upon the differences. Bitcoin is based on stateless UTXOs. Validation of the transaction is based on a stack, and the way you determine fees is by the size of the transaction. Ethereum is a stateful virtual machine. The way that you validate the validity of the transaction of an operation is, again, using the same paradigm as Bitcoin, a stack. And the way that you calculate the fees is using gas. With us, we're, again, like Bitcoin, stateless UTXOs. The way that you validate the computation of a transaction is through a natively compiled contract in your computer. And the way that you know how much that operation would cost is using the proven formal verification, the proven bounds. So people say, like, well, why go reinvent the wheel? And because we feel that if you're looking to do a certain use case, if you're looking, for example, to move around funds based on some condition, there's a better way to do it than create a big virtual machine that allows things to call into each other. So we get a few, for example, a big thing today is, transaction throughput people are talking about. So I said that this would probably be a good topic to note the differences in the paradigm. So with us, because the contracts can't directly call into each other, you can parallelize them. Let's take the example of, let's say we have 4 contracts, both in Zen and in Ethereum, and we have 5 transactions. And now we want to execute these transactions and create, let's say, a new state in Ethereum or the next block in Zen. So in Zen, what we're going to do is we're going to line up the transactions in parallel to each other, whereas in Ethereum, because everything can call into each other, you're going to line them up serially. With us also, because we're compiled rather than interpreted, because we run at the same speed that whatever software program you have on your computer runs, everything is like 10 to 100 times faster. And we also have increased efficiency because we don't have to, for every operation, move the gas counter. So in this example, for us, it would take something like 2 steps, the lowest common denominator, whereas for Ethereum, it would take something more like 10 steps, 1 for each plus the gas, but then you have to times that by 10 because they're interpreted rather than compiled. So you see about a 50x efficiency right now, right off the bat. That's it. That's what I have to say. Please come and try our software. It's currently working. You can go to alpha.zenprotocol.com to get it. We're doing a sale to support development at the end of November. So by all means, please join, and I'd love to answer any questions.
Any questions?
Hi, nice concept.
Thank you.
So where does the protocol instantiation lives?
Excuse me?
Actually, where does Zen actually live?
It's its own blockchain.
Ah, okay, I didn't get that. So in what way is it pegged to another blockchain like Bitcoin or Ethereum?
Sure. So I actually didn't have the time to get around to that in this presentation, but if you go to our website, what you can see is every block that the Zen miners create, they also create a commitment to the Bitcoin blockchain. What that means is, for example, let's say I create a smart contract that is like a call option. So I owe you money if you pay me some premium and the price of some asset goes up. You can provably pay me the premium by sending Bitcoin to my Bitcoin address that I stipulated in the contract. And the way that you would provably do that is after paying me, you would then, the Zen miner would then take the Bitcoin block that transaction was included in. He would commit that to our chain. And then from that Merkle root, you could derive a proof. You would submit that proof to the contract. And then you could say to the contract, here you go. I paid Adam in the Bitcoin blockchain. Please give me my funds.
Anyone else? Thank you very much.
Thank you.